welcome. In this video I just want to quickly do another example of Huffman encoding. And if you want to take a closer look at Huffman's algorithm, please take a look at my previous video. In this video I'm just going to quickly present his algorithm as applied to this string here. Missy is a Mississippi hippie. Again, it's a sort of a tailor-made message because it only uses a small number of characters, some of which it uses more frequently than others. So I've gone ahead and taken a look and pre-computed here, or done step one of the algorithm, which says for each character in the string, count the number of occurrences of that character in the string. So I've done that for my 8 characters here. And I'm going to go ahead and use this to perform my algorithm. Now, first step in my algorithm is to count the frequency. Second step is to create one tree with for each character labeled with its weight. Well, that's sort of what I've done here. So now I can treat these as trees and begin my iterative step, where I'm going to take the 2 trees with the lowest weight and I'm going to merge them together into a tree with weight their sum. So the total weight of this tree is now 2. 1 plus 1 equals 2. I now actually have a tie. I can merge this tree with 2 elements here to one of my other trees with 2, or I can merge these two, the m and the y, together. I think I'm just going to merge my m onto my other tree here. So the total weight now is going to be 2 plus 2 is 4. Okay, with this, now again we're going to have a tie. It looks like we need to merge a 2, my y, with a 4. And again, maybe I have a choice. Maybe this time, just because I'm going to be lazy, I'm going to say, why don't I merge it with this one here, which was already next door. And again, the total weight will be 2 plus 4 is 6. Okay, so now I need to merge a 4 with a 4. So there's no choice involved here. Looks like I'm going to get a p on here. I'm going to try and delete this one out. And again, update my weight here is going to be 4 plus 4 is 8. Okay, we got an 8, 7, 7, and a 6. Well, I'm going to go like this. Put my s here. 7 and 6 is 13. All right, continuing here, I now have an 8 and a 7. That's better than my 13. So I'm going to add it on here. All right, the last step, we need to merge our 2 trees together. And you know, I've been pretty lazy so far, so why don't I actually go ahead and redraw this tree here. And the total value here, oops, I deleted it, but it was 13, so we have 28 as our total. Now we can go ahead and, if we want, read off the values. So again, maybe I'll go ahead and write 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 0, 0, 1, 1. All right, we can already see here the way I've drawn this, my I and my S have floated to the top. So maybe we'll put those ones in first. My I have a 0, 1, and my S, we decided for a 1, 0. Notice there were a lot of ties, and if I had broke my ties in different orders, we would have got a different tree. So if you practice this by yourself, you know, pause the video and practice it yourself, then you might have got something different. That's fine. Check to see if you got the same compression as me at the end. It should be similar. Okay. What do we want to do next? Maybe P. P got 0, 0, 1, and my Y maybe next got 1, 1, 0. I'm going to leave a little space in case I want to write some more stuff over here. Space next. We got a 1, 1, 1. Let's do the other ones, the long ones over here now. So next we have maybe M. M was, looks like 0, 0, 0, 1. We have next maybe A, which is just 5 zeros. And H, similar, 4 zeros and a 1. Okay, I do want to compute sort of a compression ratio. To do that, I need to go back and look at my frequency counts again. So here, my I is of length 2, and how many of them were there? Let's double check. 1, 2, 3, 4, 5, 6, 7. There were 7, so that was 14. Next up again, 2 times how many S's did we have? I think it was also 7, but let's check. 1, 2, 3, 4, 5, 6, 7. Okay, 7. Another 14. Okay, P, it was 3 long. How many P's? 1, 2, 3, 4, 4. Oops, let's make that a times. That's 12. Okay, Y, also 3. How many Y's did we get? Looks like only 2. So that's 6. Our space, how many spaces? 1, 2, 3, 4. So we got 3 times 4 equals 12. My M, 2 times 4 equals 8. My A, hey, there's only one A. 1 times 5 equals 5. And I bet the same thing with my H, yes. 1 times 5 equals 5. Let's do a quick add here. So we have 5 and 5 is 10. 12 and 8 is 20. 14 and 6 is another 20. 14 and 12 is 26. My math here, we get a 6. 76 bits. Okay. 76 bits, probably better than we could have got with ASCII for sure. But what about a 3-bit code? Well, our 3-bit code, let's be careful again. It's going to be 28 times 3 bits is going to be 84 bits. So, yeah, shaved a few bits off there. Not bad. So again, Huffman compression is going to give us the most efficient way to compress that data. Here we showed how we can do that with a quick example, applying that to this text string here and using this Huffman tree here. Now I do encourage you, if you want to practice some more, make sure you get this down right. You could practice with this exact same string, maybe break your ties a little bit differently. You should get a different code and you should get 76 bits again if you did it right. Okay. Now also, if you want to try something different, do like I did. Pick some words that have some, shared, a lot of shared symbols. Some symbols used a lot, other symbols not used very much at all. If you can do that, you're going to get yourself a good string to be compressed. Try it with your friends, trade it up, see if you get the same answers. Great way to practice. All right, thanks for watching, and we'll see you in the next video.